Okay, everyone, welcome back. So last time we did the technical derivation of Bernoulli's, or if you skipped that video, we did the regular derivation of Bernoulli's. Either way, we learned that Bernoulli's is pretty awesome. But when do we actually use it? Well, I'm going to give you two things, because at the very beginning of this, like last lecture, we were talking about rotational versus irrotational, and suddenly we came to, we learned about vorticity, and then we started coming back to Bernoulli's again. You might be wondering, like, well, what's the connection there? Why do we talk about all that vorticity stuff and then suddenly go to Bernoulli's? Because we did say that, inviscid and irrotational, while they're connected, they're not the same thing. And so why does it matter? Well, I'm going to show you why it matters. So first off, let's say I have an airfoil right here, okay? In the second case, I'm just going to have some sort of duct. Okay, duct in one case, airfoil in the other. Now, what you will eventually learn is that if an airfoil is producing lift, okay, so lift is not equal to 0, well, that means that the circulation is also not equal to 0. And if my circulation is not equal to 0, well, that means that my vorticity is also not equal to 0. Okay, so if there's lift, there's circulation. If there's circulation, there's vorticity, which means that if I have an airfoil that is producing lift, if it's not producing lift, it might be doing this, it is going to be rotational. Okay, in this case right here with the duct, this would be irrotational, so long as I'm away from the walls. This one right here is equal to 0. This one right here, it's not equal to 0. Okay. Now let's look at some streamlines right here. So I have a streamline going over the airfoil. Kind of like that. And I have, let's just say I have several streamlines in here. Like that. Looks good. Now in the rotational case, I might have 3 points right here. 1, 2, and 3. Actually, I'm not going to do it in. Let's make those in red. There we go. So point 1, 2, and 3. So 2 of those points are on the same streamline. 1 is on a different streamline. And what we're going to find is that for this, Bernoulli's works for a streamline. So P1 plus 1/2 rho U1 squared is equal to P2 plus 1/2 rho U2 squared. That's good. That works out great. What you're not going to find is that P1 plus 1/2 rho U1 squared will not be equal to P3 plus 1/2 rho U3 squared. That is not the case. So Bernoulli's works on a streamline only if I am in rotational flow. So there you go. Now in the second case, let's go ahead and name some points again. So I've got 1 and 2 again on the same streamline. I'm going to pick a different streamline and have a point 3. And what I'm going to find here is that P1 plus 1/2 rho U1 squared is equal to P2 plus 1/2 rho U2 squared, which is actually also equal to P3 plus 1/2 rho U3 squared. So if my flow is irrotational, Bernoulli works everywhere in the flow. That is why we care about being rotational versus irrotational, because it lets me know, can I use Bernoulli everywhere or just along a streamline? Like in either case, on a streamline, it's fantastic. But in the irrotational case, Bernoulli works everywhere. I don't have to worry about, is it rotational or is it irrotational? It just works out fine. So that's it for this time. I just wanted to let you know when you can use Bernoulli and where you can use Bernoulli and why it's important to us. Have a good one. Bye-bye.